Well, good afternoon, everyone, and welcome to another colloquium for the Valongo Observatory. And today we have a very special guest.
Well, good afternoon, everyone.
I'm sorry,
Valongo Observatory.
And I'm very pleased to be able to introduce here Dr. John Mather. He is mostly known for his work on the Cosmic Background Explorer satellite, the COBE, with whom he worked with George Smoot on that, and they both won the Nobel Prize for their contributions to, in a way, confirming the Big Bang theory and finding the emission, the black body emission from the cosmic microwave background. In addition, he is a senior astrophysicist at NASA Goddard in Maryland, and adjunct professor of physics at the University of Maryland, College of Computer, Mathematical and Natural Sciences. He was listed in 2007 as one of Time Magazine's 100 most influential people in the world, and again in 2012. He's been for a while at NRC, and he is now the senior project scientist for the James Webb Space Telescope, which I know a lot of you are very interested in. And this is what he's going to be talking to us about it. So, John, thank you very much for accepting our invitation. It's a great pleasure to have you here. And now the floor is yours.
Okay, well, thank you very much for the introduction. I am here to tell you a pretty amazing story about looking back in time to the origins of everything and thinking about how did human beings come to be capable of living here on a small planet around an ordinary star. And many of you already know much of this story, but I think it's always fun to tell it. So I'm going to show you a set of pictures and a movie. I hope it plays across the internet for you, showing how this is done. And somehow these charts are jumping ahead of me already. So too quick. So here on the first chart, I show you the James Webb Space Telescope itself. Giant golden hexagon in the center is 6.5 meters in diameter, collecting light from the first stars, galaxies, and nearby planets and star-forming regions. It is protected from the heat of the sun and the earth by this gigantic sunshade. It's called 5 layers of metallized plastic that keep the sun heat and light away from the telescope. I'll show you more later, but this is an extraordinary engineering accomplishment of an international team led by NASA with the European and Canadian space agencies. And astronomers around the world are eligible to propose to use this telescope. So we've already chosen from competition the observing program for the entire first year. We're just now working out the details of exactly when is each object going to be observed. So that's why it's available for all observers, and all the results will become public promptly, either right away or within a year after observations for everyone around the world to use. So coming along to why do we care, though, I think here is my first question. Well, where did we all come from? Here's the capsule history of the universe. The early universe was very smooth and extremely hot and compressed, but it was unstable. It has been expanding and cooling, and energy is released as the system reorganizes into complex structures. So this is contrary to what people remember from high school physics, because the universe is capable of self-heating because of these arrangements, especially from gravity, which gives us negative specific heat, which means spontaneous heating. The universe is probably infinite, although there's no way to prove that. We know it's very old, about 14 billion years at least, which means that even though the existence of human life might seem to be a very small probability, nevertheless, we have observed that we are here, so we know that it's possible. We have certainly begun to understand the stored information. Every one of our cells in our body is actually a little digital computer that reads the DNA instructions and decodes those instructions and takes action, as well as interacting with the neighboring cells. through electrical and chemical signals. So we don't think of it this way, but each of us is made of roughly 30 trillion living digital computers working with each other so we can be here having this conversation. So it's an extraordinary amount of complexity that has developed over time, partly, as we know now, from evolution, which is, as I call it, survival of the lucky. When Darwin first thought about this, he realized that there was a possibility of change over time through inheritance. And immediately people at that time said, well, obviously humans are the destined masters of the universe, so we are obviously the purpose of evolution. I think these days we can look at it with a different perspective and say, actually, we're just lucky to be here, and thank you for the chances that we've been given to do what we do. Another thing we've learned about is that these digital computers and other things manage to keep things apparently stable while things are changing. So although I have all these cells in my body, most of them have been replaced over time. Most of the atoms have been replaced over time. Nevertheless, I am still myself, and biologists call this homeostasis. Nevertheless, if you wait long enough, everything changes. So I learned in school about the balance of nature, and now I think we recognize that that was an illusion. It's only because we don't live very long that nature seems to be in balance. So that's the sort of general picture. The physicist would say, well, what are the details? So we know there are four forces of physics: strong and weak nuclear reactions, electromagnetic forces, plus gravity. And they all operate according to quantum mechanics, which means that quantum mechanics governs the ways in which the little building blocks fit together. So those are the rule books of the universe, of the list of particles and how they combine together, and how much energy can be released when they do so, because the energy release governs probabilities. In particular, in equilibrium thermodynamics, we know exactly how to calculate when will water turn from water liquid to vapor or to solid, and how much energy is released in that. We can calculate those kinds of probabilities. Well, we're just beginning to work on non-equilibrium thermodynamics, in which nature always seems to find a way to increase entropy when it's possible. So as an example, we are entropy increasing machines. As some people say, well, we're here because the plants need their carbon dioxide. I think that's a little too blunt, but nevertheless, the general observation is all living things are extracting energy flows from the environment and increasing entropy by doing so. And that's how they maintain the homeostasis that keeps a pattern going for a long time. Anyway, that's sort of basic picture. So then astronomers will say, well, tell me how this early universe is unstable. And so we got onto that one a long time ago. So James Jeans gave us the calculation that says when a cloud of gas will be able to collapse and turn into a star or something. So here's a picture of stars being born in the Eagle Nebula. And the basic criterion for collapse is the gravitational force is bigger than the gas pressure. So we've been observing that this is true in many objects throughout the nearby universe, and we've been applying it as far as we can. So stepping back in time to think about the expanding universe. So back in 1929, Edwin Hubble drew us this graph. This is the first graph ever published that shows that the universe is expanding. So the dots on the graph are galaxies, as observed by many astronomers in those days, including Hubble. On the horizontal axis is the apparent distance in parsecs. On the vertical axis is the speed of motion away from us, as seen by the Doppler shift. So two observations are really important. One is that there's a trend. The more distant galaxies are going away from us with a speed approximately proportional to distance. If you divide the distance by the speed, you get the age of the universe, or apparent age, which with his data turns out to be about 2 billion years, which is incorrect because his distance scale was incorrect, and it took us a long time to find out why. Another point is in the lower left corner, there are 4 little dots that show that some galaxies are coming toward us. So that means that within the next few billion years, there's going to be a cosmic collision of some sort, where in particular the Andromeda Nebula, the beautiful M31, is going to merge with the Milky Way, and neither one will survive as a separate entity, spiral galaxy, and they will both be some kind of very much more scrambled up structure. At any rate, this was the beginning of the expanding universe story. It had been predicted before this by two people. George Lemaitre in particular was quite famous for his predictions, but only after the fact. He was a shy and quiet physicist who was also a parish priest in Belgium, as well as holding his PhD from MIT. Anyway, he worked out Einstein's equations of the universe and said the universe must be expanding. And Einstein said, no, that can't possibly be right. Nevertheless, it is right, and it took a while for Einstein to be convinced. So 1929, the expanding universe was forced on scientists by direct observations. So here's this capsule history of all of this. The universe is expanding from a hot and very compressed earlier state. As far as we can tell, there is no center and no edge, because the universe, as an infinite system, need not have an edge, and therefore it is expanding into itself. There is no empty space that we know of outside the space that is filled with material, although, to tell the truth, we cannot prove that either. We only can see the piece of the universe that we can see, and as far as we can tell, the universe has been and is very uniform, except that it's been gradually splitting itself up into galaxies and stars. So people often think, well, the universe was created or the universe began. But actually, in this mathematical picture, that's not true. The time of actually equal to zero is not included, and infinity is not a condition. Infinity is without limit. And that means, as you try to imagine going back towards the first moments of the universe, you run the movie of the universe backwards in your mind, and particles are pulled together, squeezed together, the temperature goes up and up, the density goes up and up. And eventually we say, we do not know what it should do at higher densities and pressures and temperatures, and we call that one the Big Bang. It means that there is actually not a moment of creation, because that would mean that there was time before time, and there is no such thing that we know of. So although people call it the Big Bang, it is not a big firecracker. A big firecracker has a location in space, and it has a beginning in time, and neither of those is true of the expanding universe that we see. So it has been poorly explained by most science journalists and by many scientists, so it's not surprising that most people are confused about this. Nevertheless, this is what the mathematics tells us. So how would we know this is true? Well, of course, we take pictures. This is one of our great space observatories, the Hubble Space Telescope. It is 31 years old already, and it is working very well because we've sent up astronauts to fix it and upgrade it 5 times. And it will show you some of the examples of what it's done to support this picture. But first, I want to show you the Webb telescope, which is extending the observations of the Hubble. So here is the great Webb telescope. I'm not sure if my pointer will show, but here's the great hexagon, 6.5 meters across. It is folded up for launch, and I will show you how that is done. It's protected by this gigantic sunshade. It's not really blue as it is in the picture. And the observatory is being constructed by an international team. It's led by Goddard Space Flight Center. Our major large contractor is Northrop Grumman, concentrated in Los Angeles, California. And we have pieces that have come to us from around the world, from the University of Arizona, from the European Space Agency, from Jet Propulsion Laboratory, and from Canada. And so all of these have now been assembled into one unified observatory, and they are all currently in California, being folded up and prepared for launch. Telescope is going to be cold in outer space. When astronomers saw their results coming back from Hubble, they said, that is beautiful and wonderful, but it still doesn't answer all of our questions. And there is one huge area of open science. That is, things that we cannot do yet because we don't have the right equipment. So the committee wrote a book that said, please build us an infrared telescope that's capable of seeing farther back in time and is more sensitive and powerful than the ones that we've had before. So this is it. This is the answer to those prayers. So the telescope operates around 50 degrees Kelvin, very cold, and that is so that it does not emit infrared itself. Observatory is planned for a launch in November from French Guiana in South America, not far from you. That's because the European launch facility is there quite near the equator, so it's a good place for that. And Europe is buying the rocket, and that's why we're going from their spot. So how did this all happen? Well, here is the author of the book. Alan Dressler wrote the book with a committee that said HST and beyond. HST is the Hubble Space Telescope, and they wrote a book saying, please build us a new one that's even more powerful. It was a little while later that he met with the head of NASA. Dan Golden announced to the Astronomical Society here that the little book was not nearly ambitious enough. Please ask for something more powerful. We're going to build it, he said, and it's going to be bigger and better. So he got a standing ovation after his speech. And so, of course, we concluded this was going to be very popular if we could ever do it. So then more and more books were written saying, please build it like that. And so we are now planning for a launch. The picture hasn't been quite updated yet because we just recently learned that the launch rocket may not quite be ready on that date, but quite soon after, we think. So what are the great themes of science that we're planning to explore? We have 4 in mind, but this is not all. The first big question was, how did the first stars and galaxies get formed? And how did they light up after the Big Bang? So in particular, what was it that liberated all the ultraviolet light that was capable of reionizing the hydrogen and helium that had been in existence since the cosmic decoupling when the universe was much younger? How did the galaxies grow? We have many wonderful simulations showing that gravity pulls together small bits to make large galaxies. It would be great if we could find out the story and see how true it is. And in particular, how did the first black holes grow at the centers of galaxies? We will be looking inside clouds, such as the one in the lower left, where stars are being born today. Our view is obscured by those dust clouds, and we cannot see inside to understand how the stars are being born. But infrared light is capable of going around the dust grains and letting us see inside. Finally, on the lower right corner, we illustrate that we're very interested in planets around nearby stars. This particular picture shows you one planet orbiting a nearby star. But of course, now we know that most stars have planets, and it's just very hard to see them. So we'll try with a Webb telescope. So here's a science team, many scientists that you may have come across their names already, distributed across Europe, Canada, and the United States. And this is not including, of course, pictures of the many thousands of engineers and technicians and managers who are actually making this observatory possible and putting it together. So how does it work? Here is a diagram of the great telescope itself. It is similar to a Cassegrain telescope, but it has a third mirror called a tertiary mirror, which corrects for the aberrations of the Cassegrain telescope and gives a much better image quality. Even though this is a very, very short focus primary mirror, the picture also illustrates that we are making the primary mirror out of 18 hexagons of beryllium. Beryllium is extremely thin, about 2 millimeters thick, cut with a milling machine, and then polished to the correct shape when it will be cold. So the operating temperature is going to be around 40 Kelvin, maybe 50. So we have to polish the mirror pieces so that when they are cooled down to the low temperature, they will be the right shape. And we've learned how to do that. We have a a very general purpose instrument package that includes cameras and spectrometers covering the entire wavelength range from 0.6 microns, which is red and you could see it, all the way out to 28 microns, where we are just barely able to see the hydrogen molecular line at 28 microns. So a very most difficult instrument to build, well, they were all difficult, but the near-infrared spectrograph was especially notorious for the remarkable design that we required. We said we need to be able to observe 100 separate galaxies at one time with a spectrometer. So this is done with micro shutters that can be commanded open and closed by out of a choice of 250,000 little shutters. So how sensitive is this observatory? If you are a square centimeter object at the distance of the moon, then we are able to take your picture with a time exposure. A bumblebee is a small American insect, but this is just a 1 square centimeter example. You could see the reflected sunlight and the thermal emission from such a small object. The bright objects like Mars are more of a challenge to us because the photons come in so quickly that we have to restrict them and usually only take a small piece of the total picture at once. Nevertheless, we have ways so we can look at all objects from Mars on outwards in the solar system. We can also observe bright stars to see when small planets go in front of them. So how sensitive is it compared with other observatories? This is a set of curves where the bottom of the chart is the best. And so we are showing here that this is an extremely sensitive observatory. And that the Webb telescope is more sensitive than all of its forerunners and precursors by at least 1 order of magnitude at most wavelengths. So that's one of the reasons we expect to see something no one else has ever seen using this equipment. We have chosen the observations to be done in the first year. So some were given to the people who helped build the instruments. Some were given in response to a competition where people proposed to observe objects and then release the data immediately. And some, just very recently chosen, were based on proposals from observers around the world. And I don't know if any of you proposed, but you could have. So we have received proposals on all of these topics. You see that about a quarter of them were about exoplanets, about 20% about galaxies. And anyway, it's a very remarkable range of topics that we chose from, and over 4,000 unique investigators participated in this process. So you can learn more about all of this by looking at our YouTube channel. There's a whole variety of things available on the websites, which Google search will find for you. So what are we going to look at? Here is a picture taken by the Hubble Space Telescope. It's called the Hubble Deep Field. And what we see in this picture is a large number of very faint galaxies, some of them irregular, some of them very tiny red dots. And this is the kind of picture that Hubble astronomers use to say, we're very happy with the Hubble, but it still is not powerful enough to see the very first galaxies. We need something that's more powerful and can see longer wavelengths. So the only object in this image that's a star is the one in the lower right corner with the green and red spikes sticking out of it. All the rest are galaxies. What are those first galaxies? Story goes that the first ones formed from very rare density fluctuations in the primordial universe, and that they were only able to cool themselves by molecular radiation from hydrogen. That took very high densities to succeed. So this tells us what the theory will offer us about what the first galaxies will be, that they could be forming as early as a redshift of 30, where those very first stars would form and would begin to dissociate the hydrogen around them. We will be taking pictures. This is a diagram showing where we're going to be looking as an example, pointing the various instruments at some very famous spots that we have already chosen to observe with other equipment. So we will be filling in many of the same spots, only more. So another thing we have to do is to take spectra of early galaxies. This one shows that typical spectrum of an early galaxy can be obtained quite well, and the grid work display that you see there illustrates the micro shutter array, which says we can open up a shutter or a set of shutters to let in the light of a particular galaxy into the spectrometer. We will be looking into the dusty dust clouds that I mentioned to you earlier. And here is an illustration comparing the visible appearance with the near-infrared appearance as seen with Hubble. And you see they're quite different. The dust cloud is much more transparent at infrared wavelengths, and it allows us to see much deeper in. But we still see that we cannot see all the way into the densest parts of those dust clouds. The Webb telescope will be able to see much farther in, but I can't draw you a picture yet. I don't know enough about what it should look like. Here is an example showing the difference of the Carina nebula as we change the wavelength from the visible into the infrared. Dramatic changes there. We will be looking at solar system targets. Europa, a satellite of Jupiter, has an ocean covered with ice. It has warm water coming out occasionally in the cracks between the ice pieces. And we are sending an observing mission to circle the solar system, circle the Jupiter system, and observe Europa close up. In particular, we want to fly the probe through the water jets that are coming out to see whether they have organic chemicals in them. We will be flying out to Titan, a satellite of Saturn. We know Titan has very interesting surface with lakes and rivers, and it has rain, all formed by hydrocarbons, methane and ethane. It has clouds, it has sand dunes, it has weather. The surface under the solid surface under those hydrocarbons is water ice. So this is certainly going to be an interesting place to explore. Helicopter to fly around a little bit on the surface of Saturn. We will be looking at exoplanets. Exoplanets can be observed either directly as little images, which only works if they're very bright, or alternatively by watching a star be partially blocked by a planet that goes in front of it. So from this method, we already have a catalog of many thousands of planets around other stars, and we know when to expect them to transit in front of their stars. So from the geometry, we can determine the size of each planet relative to its star. And from the orbital periods, we can calculate the temperatures of those planets. From the observations, though, we hope to also get spectroscopy and chemistry. So some of the starlight goes through the atmosphere of the planet on its way to our telescope, and we can analyze the molecules that absorb some of that light on its way. So we'll be especially looking for signs of water, also carbon dioxide and methane that may occur in those little planets out there. So we have a plan, and we know which ones we're going to look at. We don't yet know what we'll find. There will be an early release science program. We have chosen the teams to do that, and they represent many investigators. And if you want to find out more about them, there were several webinars you can find on the internet to tell you what those are. You'll be able to see what we're planning to give you right away. We will be looking at places like this where galaxies are just beginning to light up. We have many programs chosen in this early release science program. So I'm just illustrating a few bits from that. So, yeah. In particular, we will be looking at gravitational lenses. There are a number of locations in the sky, actually many hundreds of them, where we know that the gravitational force of a cluster of galaxies or of an individual galaxy is capable of focusing and distorting the image of a more distant object. So this is like having an extra lens to make your telescope more powerful. So we will certainly be looking at these locations as illustrated here. So in this illustration, there are galaxies that are magnified by a factor of up to 40. So certainly will be exciting to do that. We will be looking into the nuclear cores of galaxies. There's a black hole in the middle of almost every galaxy, and we'd like to know how that works. We have the equipment to find out. We will be doing astrochemistry, studying the molecules and atoms that are in the space near stars that are being formed, near stars that are blowing up, as the Wolf-Rayet stars do. We'll be looking at how the energy that comes out from new stars, massive stars, changes their chemistry of the surrounding material and can therefore affect the way new stars are going to be born near those other stars. Be looking into that. We will be looking, as I mentioned earlier, at the planets. We expect the solar system planets to look a little different with the Webb telescope because it can pick up wavelengths that we can't see otherwise. We will be doing coronagraphic studies, which is to say we will block the light of the star to enhance the visibility of a faint planet next to it. The picture in the upper left, though, shows an illustration of a planet orbiting in front and blocking the light of a star and showing how much the different molecules in the atmosphere of such a planet can already be known to change the spectrum that we see. So here's another illustration showing the planets that we're going to be looking at, ranging from Earth-sized little planets all the way up to big hot Jupiters that are close to their stars. It will be very exciting for the planet programs, and we expect to have many surprises. So now let me show you how we prepare the Webb telescope for launch. We built the telescope part up itself at Goddard Space Flight Center and attached the instrument packages that had come from around the world. So now in my upper left picture, I show you the golden hexagon with a folded up secondary mirror. The instrument package is behind that. After we put it together, we put it in a protective plastic tent and supported it and took it over to a shaking device. We were able to apply 50,000 pounds of vibration force to this telescope in order to simulate the dangerous launch that it will have. When we have finished that, we put it in a shipping container, put it in an airplane, very large airplane called a C-5C, and flew it all the way to Texas. So in Texas, in Houston, Texas, we have the space agency has a gigantic vacuum tank, which was originally used by the Apollo astronauts to prepare themselves to walk down the ladder of their space capsule onto the surface of the moon. We had to change the vacuum tank to make it capable of getting very cold so we could simulate the true conditions the Webb telescope will see in outer space. So after it survived that, we took it to California on the airplane, and it has been assembled there in Los Angeles with the rest of the observatory. And we have been folding it and unfolding it and testing it. We are now in the process of folding it up for the very last time and putting it into the, we will be shipping it somewhere in August, shipping it on this boat, going through the Panama Canal on its way to the launch site in French Guiana in Kourou. And after we have finished preparing it there and make sure everything is still in good condition, the launch facility will press the launch button and it will go up and it will send about 1.5 million kilometers into space. And we'll show you where that is. And finally, it will unfold way out there. Where are we putting it? We're putting it around the Sun-Earth Lagrange point 2. As you know, the Lagrange points are places where the combined gravity of the Sun and the Earth can pull the object around the sun once a year. So we will put ours at the Lagrange point 2, because from that location, the sun, the earth, and the moon are all in one direction, and you can protect the telescope from the heat of those objects with a one-sided umbrella. So here's our scary movie. We will be deploying in the observatory by remote control commands shortly after launch. The first things that we do, of course, is to unfold the solar panels so we get electricity, and the transmitting antenna so we get the data back. Then over the course of the next 2 weeks, the rest of this deployment will occur. The telescope will be unfolded, the protective sunshade will be unfolded, and after 2 weeks, it's about in the right place. It's an extraordinarily complex design, but it is, despite this enormous complexity, it is not the most complex one that our company Northrop Grumman has ever built. This is all done by remote control, and so you say, how can we possibly be sure that it will work? Of course, you can never be sure, but what you have to do to be sure is, number one, test and test and test. Number two, examine the design extremely carefully. Get all of your friends to come tell you why you might be wrong. And number three, make sure you have 2 of everything when you possibly can. So every motor has 2 different ways to turn it, 2 sets of electrical windings and 2 electronic controllers for every motor. So there it is as it will be unfolded in space, but it's still not quite ready for operation. After that is unfolded, we have to spend the next 6 months focusing the telescope and verifying that everything functions correctly. So if you want to know more, we have many websites you can follow. This is an example of some of them. But of course, you can find everything by Googling James Webb Space Telescope or JWST. Following this, I think it's interesting to speculate what will astronomers do next. So, of course, astronomers are not only interested in building telescopes in space, we also have ambitions for telescopes on the ground. Now 2 of these 3 are being prepared for operation in Chile. The one that's farthest along is the European Extremely Large Telescope, 39 meters in diameter, and we're expecting it to be operational in about 5 years. So that size of 39 meters is 6 times the diameter of the Webb telescope, and it is so large that it will do things that no other equipment has ever done, or maybe this is as far as we can get into the future. Anyway, it will be extraordinarily powerful. The other 2 will also be powerful, just smaller, and each will be used for its purposes that are for which it's most best suited. So, among other things, the giant telescope is capable of better angular resolution if you can compensate the atmospheric turbulence, and of course better sensitivity if the atmosphere is clear enough. So here's the principle that we use for that. The turbulent atmosphere damages the image quality, as you know. And in fact, the telescope that you can buy or build yourself has about the same image quality as a very large telescope because of the atmospheric turbulence. So back in 1953, it was imagined that if we could find a point source, a star in the sky, and use it to focus the telescope, we could compensate for the turbulent atmosphere if you could measure the variations of the atmosphere. So this has been developed since then into a pretty high technology solution, with the result that you can get nearly perfect image quality if you can do this trick, but it's complicated and difficult. The right-hand side, by the way, illustrates that you can now get this technology if your eye doctor needs to see into your eye, because, of course, the surface of your eye isn't perfect. The reason that I like showing this chart is that the person who learned how to polish the Webb telescope mirrors to the correct shape is also the same person who invented the latest edition, the latest version of this technology for use by eye doctors. So now I want to wrap up with a concept I'm currently working on called the orbiting configurable artificial star. This is a laser beam in space that can shine down on a telescope on the ground to enable it to have something to focus on. So we've been studying this for about a year, and we believe that it can be done and that it will be very powerful. So all of the things that you can't do because of the turbulent atmosphere, we think we can manage that. An even more difficult challenge, which is not impossible, at least in principle, is to observe exoplanets by flying in the same way to fly a star shade. A star shade capable of casting a very good shadow on the telescope would enable the kind of image that I'm showing you on the right, where in 1 minute exposure with the European Extremely Large Telescope, you could get a nice picture showing Earth, Venus, and Mars orbiting around their star. So at least logically speaking, it is not impossible. It's certainly not technically possible yet, but I think that it will be exciting if we get to try. As an example that I want to show you of how good it could be if you could do this, here is a spectrum of another Earth or a Jupiter or a Neptune or a Venus seen at a distance of 5 parsecs with this kind of equipment. And what we see here is that in the lower panel, there's a little blue curve, which is the spectrum of a simulated Earth. And it shows 2 spectrum bands with strong oxygen lines and 4, I think, spectrum bands of water absorption. So it turns out that this is capable of detecting things that we would consider markers of a living Earth if they could be found. So it is not impossible. Whether this is the equipment that astronomers will ever decide to build, that's another subject. But I just wanted to put it here to stretch your imagination to say then many things which we believe to be impossible are not impossible. So let me stop here, and I'll be happy to talk with you and answer questions. So thank you.
Thank you very much, John. That was great. And we already have some questions here. And I think one question that was certain to pop up is this one. I'm pretty sure this will be mentioned, but and what's the timeline looking for the launch, the first data collection and all that? So
yes,
maybe including the 6 months.
Yeah, we will be planning to ship the observatory to the launch site in August, and we should have it ready for launch by the end of October, and probably the rocket will be ready soon after that. So mid-November, I think, or maybe late November for the launch date. Then 6 months after launch, we should be able to say, here it's all working, and here are the first observations that we can show you with a giant press release of some sort. And, then we'll start in on the observing program that has been proposed and agreed to. And so within, I think, a few weeks of opening the observatory, then we will see some beautiful pictures coming. That's the plan.
So probably around mid-2022, something like that.
Yes, that's I think what we'll see.
And one question that I would follow up with is in terms of the lifetime, because I do believe that the minimum lifetime expected is 5 years, but what is the realistic expectations on that? Yes,
we are carrying fuel for at least 10 years of operation and hoping for more. So it's realistic to hope for 10, 15, 20 years of operation. Nothing is supposed to wear out. But fuel will run out sometime.
That's great, because I do know that the competition is great, and so it's good to hope that this will be there for a while.
Yes.
And also, I think on that line, there's a question by Denise, who's also a professor in our institute. She's asking, since the first cycle of the JWS proposals, did researchers took advantage of this window of opportunity, and will this window? I think she's asking in terms of the timeline for the proposals in cycle 2, etc.
Yes, I think that we will be announcing the call for new proposals about a year before well, I think we start the proposals a few months after the launch, after the first data start to come in, and I don't remember the exact date. But she was also asking about joint proposals with Hubble.
Yes. Sorry about that. Yeah.
So I don't think we had very much in that area yet. There are a few cases where a simultaneous observation with Hubble and the Webb could be interesting. So we don't have very many, but there are a few that would be interesting.
And in terms of the lasting, people are asking, is there a chance that it could last as much as Hubble then?
I suppose there's a chance, but Hubble is over 30 years old now, so I think that's unlikely.
That would be great. Actually, is there the possibility of continuing on a warm mission like Spitzer did?
No, there's not actually a possibility. The telescope is already cold because of its own design. The telescope cools by radiation to outer space. So it does not run out of refrigerant.
Okay.
The way that the Spitzer Space Telescope did. It does have a refrigerator to cool the mid-infrared instrument to 7 Kelvin. But that also does not run out. It's not a stored cryogen. It is a closed cycle system.
Oh, I see. Okay.
So it should last forever until some electronic or mechanical part fails.
Okay. Oh, that's good.
So that's then. But we do use the fuel. We should say why we use fuel. Fuel is required for two purposes. One is that the orbit is unstable. So once in a while we have to apply thrust to make sure we don't fall off the Lagrange point area. And the other purpose is to manage the angular momentum. Sunshine presses on the starshade, on the sunshade, and tries to turn over the telescope if it's not balanced over the center of mass. So we have to compensate for that eventually.
So let's see. Let's hope it lasts many years. I know that people are very excited about it. There's a question here regarding the design of the instrument. Was there any special reason to choose a mirror made of several hexagons and not a curved mirror like the Hubble mirror? Yes,
we choose hexagons because they are you can fit them together to make a bigger hexagon. Without very many gaps in between. So it's the technology of making the mirror very large and make it out of hexagons that makes the bigger mirror a hexagon too. We could have cut off the edges to make it rounder, but that did not seem to be helpful.
I think there are many, all the big telescopes, at least on Earth, I know that they're hexagons, and I think James Webb is the first segmented mirror in space, right?
Yes, it is.
Okay. Now there's a science question here. Luigi Santana, who used to be a PhD student, now he's a doctor. He's asking about James Webb deep fields. I know you mentioned one by Steve Filkenstein in your talk. Can you talk a little bit more about that?
Yes, absolutely. It was one of the initial desires. The reason that we built the telescope was to get more deep fields like the ones that Hubble got. So the answer is absolutely yes. Everybody wants them. Not only because of the cosmology, but because of all the other things that may turn up with a long exposure. So it's now only a question of exactly which ones and when. So we will probably not do them right away. We have to learn how to do them. The Hubble deep fields were not observed right away because we had to learn how to observe so that the noise would average away. When you average 10 pictures together, it isn't always 10 times better. So we need to make sure that there's no reason that we're wasting our time doing it some wrong way. So I have to learn first and then do it.
Hopefully they will come soon. I know that a lot of extragalactic people, especially, are very excited about the prospects of observing with the deep field in the James Webb. I'll allow some little more time if someone has more questions here. I'll take the chance here to announce that there is going. John mentioned the possibility of proposing. I think it's good to remind everyone that people in Brazil can propose as well. We do have 2 PIs from Brazil that were approved in cycle 1, and we are planning to organize a a workshop here in Brazil. It was supposed to happen last year. I was supposed to organize it, but then the pandemics came and everything went out of whack. But we do plan to have a workshop. It's probably going to happen sometime in September. So if you're interested in applying for James Webb Time, this is a good opportunity to learn the basics and the intrinsics of how the proposal process works and the specific instruments and all that. So if you're interested, keep an eye out for announcements from our university.
I'm delighted to hear that, because we never know in advance who's got the best ideas. So we welcome your ideas.
Exactly. So it's good to help people put those ideas out there. Carina Menendez de Mestre, also a professor in our institute. She's asking, is there a James Webb data archive, or will there be a data
Yes,
archive?
there will be. It will be in the same location at the Space Telescope Science Institute that we keep the Hubble data. And so, yes, we'll be able to access everything.
Okay, so
There will some of the data will be released immediately, and many of the specific observations are kept for 1 year for the private use of the investigating team, and then they become public. But it will all become public.
So it's a 12-month proprietary period then.
Yes.
Yeah. That's good to know. I know, again, a lot of people will be interested in that for sure. I have one last question here. I think it's a very nice question to wrap up your talk. Marco, who's a student in our institute, he's asking, the James Webb is expected to see very far in an age of galaxies should not exist as we understand now, so certainly the first light. What could happen with our present notion of the universe if we do find galaxies this far? So what should we expect to see?
Yeah, good question. I would love to have that surprise. Because we have a calculation that says the early universe was filled with random fluctuations with a Gaussian distribution and a certain spatial spectrum and no correlations. So if that's true, then we should be able to calculate when the first galaxies could exist. And if that's wrong, that tells us something that we would be very surprised about. It would mean that there was some primordial structure that has not shown itself yet, that nevertheless affected the formation of the first objects. Another thing that we might learn is about the formation of the first black holes. It's still a huge mystery why every galaxy has a black hole, and why is the mass of that black hole roughly proportional to the mass of the stars in the bulge of the galaxy. So it tells us something, but we have not been able to observe the process. So we don't know when it began. Did it begin, for instance, with the first generations of stars turning into black holes themselves, and then merging together to form bigger black holes, which now migrate to the center of a galaxy? Or did something else happen? Did the black holes consume gas directly later? So all of this is mysterious to me, and I think for all of us. So we have a hope to answer that question by seeing the process earlier on.
So yeah, there's certainly very exciting science that is coming out of James Webb, and I think we're all very excited. If you do have the time, there's one last question that came out here again by Carina. I think it's a good question, and she's asking about the blind approach to the proposal review. How did it turn out?
Yes, so she's asking about what we call double blind, where the proposals are written in a way that no one can tell who wrote the proposal. and the reviewers do not know who wrote the proposal. And so the aim is to be as fair as possible to new ideas and new teams, and particularly to groups that might not be chosen otherwise because somebody doesn't think those are such good groups. So we'd like to be to solicit the best ideas, the most creative ideas, rather than to find people who have been doing this all their lives. So we are very pleased with the results. It has improved the odds for selection of young people. Something about 9 or 10% of the proposals were led by graduate students. So in old days, you would say, well, I need to get an old professor to send in my proposal. Now we say, well, you did the work, you send it in. And so I'm very pleased with that.
Okay, that's great news. This is something that I know started with Hubble a few cycles ago, and
Yes,
it has been a great success. So
yes, I'm really pleased with that.
yes, no, I think it's an incredible idea, and as you said, it more chance to younger people and to against biases. So I think that's it. I think we went through all the questions that we had here. I would like to thank you again very much for your presence and for talking to us here. It was a great pleasure to
yes,
to hear
well,
your
a pleasure to talk with you and to talk with you again, and to meet your students and faculty. So best luck on your next round of proposal writing.
Yes, definitely. We'll keep working on that, and hopefully the workshop will stimulate people to write their own proposals as well. We'll have a lot of Brazilian proposals in the next cycle.
So yep. So and we won't be able to know if it's Brazilian or not.
Exactly. But again, thank you very much, and for the people who are watching this, thank you for your presence here. And I hope to see you next week again. We have a talk by Jean-Claude Bourret from France. So hopefully we'll see you here again next week at the same time. Thank you very much, and thank you, John.
Thank you all.
Bye-bye.